Assalamualaikum and good day. This video will explain about the dual simplex method. There are certain kinds of sensitivity analysis naturally lead to the uses of the dual simplex method. For example, to find the new optimal solution when a constraint is added to an LP or when a right-hand side of a constraint has been changed. If the right-hand side of a constraint is changed and the current basis becomes invisible, means if there is any constraint in which the right-hand side is negative, then the dual simplex can be used to find the new optimal solution. There are few steps to solve a maximum problem when the tableau has one or more negative right-hand sides and each variable in row 0 has a non-negative coefficient. First, check the right-hand side of each constraint. Then, the basic variable with the most negative right-hand side will become the leaving variable. Next, calculate the ratio for each variable that has a negative coefficient in the pivot row. The ratio formula is the modulus of coefficient of the variable in row 0 divided by the coefficient of that variable in pivot row. Choose the variable with the smallest ratio as the entering variable. Finally, apply the EROs to update the tableau. Now, let's discuss. This is a maximum problem because each variable in row 0 has a non-negative coefficient and the variable x1 has negative value. Then the dual simplex method may be used to find the new optimal solution. X1 must leave the basis. And row 3 is the pivot row. Because there are two negative coefficients in row 3, we need to calculate the ratio to determine the entering variable. Ratio for S2 is 10 divided by negative 3 over 2 and we get negative 6.667. The ratio of this variable is 6.667. S3 has ratio 20. The smaller ratio is the S2 ratio. We use ERO to enter S2 into the basis in row 3. ERO for row 3 is negative 2 over 3 times R3. And we get new row 3. ERO for row 2 is R2 minus 2R3 and R1 minus 2R3 is ERO for row 1. ERO for row 0 is R0 minus 10R3. Then we update the tableau. This is an optimal tableau with the new optimal solution to the problem. The solution for this problem is x1 equals to 0, x2 also equals to 0, x3 is 24, s1 equals to 40, s2 equals to 2, s3 is 0, and z value is 360. Now, let us solve exercise 4.3. This tableau shows each variable in row 0 has a non-negative coefficient. However, the current basis is invisible. The variable S2 is the most negative one, so S2 must leave the basis. And row 2 will be the pivot row. Because S1 has the only negative coefficient in row 2, S1 will enter the basis. We use ERO negative 2 times R2 for row 2. So that S1 will enter the basis in row 2. These are new elements in row 2. Next, we update row 0 and row 1 by these EROs. R1 minus 1 over 2 R2 and R0 minus 2 R2. New row 0 and row 1 are shown in this tableau. Each right-hand side is non-negative and all coefficients in row 0 are also non-negative. Therefore, this is an optimal tableau. The optimal solution to the problem is x1 equals to 0, s2 equals to 8, s1 equals to 4, and s2 equals to 0, with the z value is equal to 32. Now, please do exercise 4.4 as your homework, where you need to solve this problem or find the optimal solution of this LP problem by using the dual simplex method. I will give you some guidelines on how to solve this problem. If the question asks you to find the optimal solution of this LP problem without stating any method, then you can solve this problem by using either BI method or two-phase method. This is because, let us transform this problem to a standard and Tableau form. First write the constraint. We have subject to 3x1 plus x2 plus x3. Okay, since the first constraint has greater than or equal to sign, therefore we need to subtract an excess variable from the left-hand side of this constraint. Minus E1 equals to 3. Okay, for the second constraint, we have negative 3x1 plus 3x2 plus x3. Also, because of the sign is greater than or equal to, then we need to subtract excess variable 2. Okay, equals to 6. And for the third constraint, we have x1 plus x2 plus x3 and plus s3 equals to 3. Okay, since the sign of the third constraint is less than or equal to, so we need to add a surplus variable to this constraint. Then include these new variables in the sign restriction. x1, x2, x3, E1, E2, and S3 are greater than or equal to 0. Next, find the basic variable for every constraint. As we can see here, x1, x2, and x3 cannot be basic variable in either constraint 1, constraint 2, or constraint 3. Okay, therefore, we need to choose other variable to be the basic variable in these constraints. E1 is not the basic variable for constraint 1 because the coefficient of this variable is negative 1. Therefore, we need to add an artificial variable A1 to this constraint so that this variable can be the basic variable in constraint 1. Okay, next, same goes to this constraint. There is no basic variable in constraint 2. Therefore, A2 is the basic variable for constraint 2. And in constraint 3, S3 can be the basic variable because this variable only exists in the third constraint and the coefficient of this variable is 1. Okay, since we have A1 and A2 in constraint 1 and 2, we need to include these variables in the sign restriction. Okay, because we have artificial variables in first and the second constraint, we can solve this problem either by using Big M method or two-phase method. If we will use Big M method, the objective function of this problem becomes minimize z equals to 3x1 plus 2x2 plus x3 plus ma1 plus ma2. Okay, because we need to penalize the objective function by adding ma1 and ma2 to the objective function if the problem is a minimization problem. Okay, if we decide to solve this problem by using two-phase method, the objective function of this problem in phase 1 is minimize R equals to A1 plus A2. Then, by using this objective function, together with these constraints, then we can solve the problem. Okay, but since the question wants us to solve the problem by using the dual simplex method, then we cannot use a big M method or two-phase method. We need to use dual simplex method. Okay, in dual simplex method, we need to make sure that the optimality condition in the objective function is satisfied. Where if the problem is minimization problem, all coefficients in the objective function are non-positive. Okay, from this one, okay, we have minimum z. We want to minimize z. We need to make sure the coefficient in the row 0 are non-positive. And also exists negative right hand side in any constraint. Okay, so now let's look at this model. First, we rearrange the objective function. We have minimize z minus 3x1 minus 2x2 minus x3 equals to 0. Okay. Check the optimality condition in this objective function. Okay, since the problem is to minimize z, okay, we can see that coefficient of x1, x2, and x3, all of them are non-positive. Therefore, the optimality condition, one of the optimality condition has been satisfied. Now, look at the constraint. There is no negative right-hand side. But since we need to solve this problem by using the dual simplex, we need to create the negative. We need to change the right-hand side of any of the constraint becomes negative. Since we can't use artificial variable in the dual simplex method, therefore we need to do something to the first and second constraint, because the first constraint will have artificial variable if we change this constraint to the standard form. Okay, so because we don't want any artificial variable in the constraint, we need to change the sign of this constraint. Okay, if we change the sign of this constraint, we need to multiply the first constraint by negative 1. Okay, if we multiply the first constraint by negative 1, we will get negative 3x1 minus x2 minus x3, and the right hand side is negative 3, and the sign is changed. Okay, from greater than or equal to, it becomes less than or equal to. Now we have negative right hand side. Okay, same to the second constraint. If we change the constraint to the standard form, okay, we need to subtract an excess variable, and then we need to add an artificial variable. Okay, then we cannot use dual simplex. So to avoid using artificial variable as basic variable, we need to change the sign of this constraint. Okay, let's multiply this constraint by -1. Okay, we will get -1 times -3 is positive 3x1 minus 3x2 minus x3, and the right hand side is -6, and also the sign will change to less than or equal to. And for the third constraint, we don't have to do anything because the sign already less than or equal to, and when we transform to the standard form, we have s3 as the basic variable. Okay, we just rewrite the constraint. We have x1 plus x2 plus x3 less than or equals to 3. It's negative. Okay, now we can solve this problem by using the dual simplex method. Since we have all negative coefficient in row 0 and exists negative right hand side, okay, in the constraint. So we can solve this problem by using the dual simplex method. Okay, that's the guideline to find the solution of this problem. Now, let's discuss example 4.6, where we need to find the optimal solution of the problem in example 4.4. When Toiko increased the availability of operation A by 50 minutes, so D1 is 50, and decrease operating time in operation B and C by 20 minutes respectively. Okay, so we have here D2 is -20 and D3 also -20. In example 4.4, we get the value of x2 equals to 130, x3 equals to 220, and s3 equals to -120. Okay, since one of the basic variable is negative, therefore the current solution is no longer feasible. We need to find the new optimal solution for this problem by using the dual simplex method. First, we need to get the optimal tableau of the original problem. This is the optimal tableau of the original problem. From this optimal tableau, we can see that the value of x2, x3, and x3 have been changed. Okay, from 100, it becomes 130, x3 is 220, and s3 is -120. And for the right hand side, z is equal to, by using the dual price, okay, the equation of z is 1350 plus d1 plus 2d2 plus 0d3. Okay, we substitute D1, D2, and D3 into this equation. We will get Z equals to 1360. Now we can see that this tableau is not the optimal tableau since we have negative value of the one of the basic variable. Therefore, we can solve this problem by using the dual simplex method. Choose the variable with the most negative right hand side as the leaving variable. Then choose the entering variable. Okay. In the pivot row, only S1 has the negative coefficient. Therefore, S1 is the entering variable. S1, we replace S3 as the basic variable in row 3. X2 and X3 remain as basic variable in row 1 and row 2 respectively. So this one is X2, X3 and S1. Okay, we need to change the coefficient of S1 in row 3 from -2 to 1. Therefore, the ERO for row 3 is -1/2 times R3. We multiply every coefficient in row 3 by -2. Okay, we will get -1, 0, 0, 1, -1/2, -1/2, and the right hand side is 60. Since the coefficient of S1 in row 2 already 0, we rewrite the whole row 2. Okay, we have here 3/2, 0, 1, 0, 1/2, 0, and 220. Okay. For row 1, we want to change this coefficient to 0. Therefore, the ERO for row 1 is row 1 minus 1/2 times row 3, new row 3. By using this ERO, we update row 1. For coefficient of X1 in row 1 is -1/4 minus 1/2 times -1. So we get 1/4. X2 is 1 minus 1/2 times 0 is 1. X3 is 0. S1 is 0. S2 is -1/4 minus 1/2 times -1/2. So we get 0. S3 is 0 minus 1/2 times -1/2. So we get positive 1/4. And the right hand side 130 minus 1/2 times 60. So we get here 100. Okay, now move to row 0. Okay, to change this coefficient to 0, ERO for row 0 is row 0 minus row 3, new row 3. Okay, row 0, the coefficient of x1 in row 0 is 4 minus negative 1. So we get 5. 0 minus 0 is 0. 0 minus 0 also 0. S1 also 0. S2 is 2 minus negative 1 over 2. We'll get 5 over 2. And S3 is 0 minus negative 1 over 2. So here is 1 over 2. The right hand side, 1360 minus 60. So the right hand side of row 0 is 1300. Okay, now check the optimality of this tableau. Okay, since the problem is to maximize the revenue, we need to make sure each variable in row 0 has non-negative coefficient. Okay, since there is no negative coefficient in row 0, okay, one of the optimality condition has been satisfied. Now, check the value of every basic variable. Okay, we have no negative right-hand side. Therefore, we can declare this tableau as new optimal tableau. Okay, the new solution for this problem is x1 is 0, x2 is 100, x3 is 220, S1 is 60, and the new Z value is RM 1300. This is the new solution when Toyko changed the operating hours in operation A, B, and C. Now, please do exercise 4.5 as your homework.
Okay, Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. So we continue our lesson with the last subtopic for chapter 4, which is sensitivity analysis with LP solver. So computer programs designed to solve LP problems are now widely available to obtain optimal solutions. Most large LP problems can be solved with just a few minutes of computer time. Small LP problems usually require only a few seconds. There are several LP solvers that are commonly used, such as Simplex, Lingo, Tora, and etc. You can Google to search for more available LP solvers online for free. LP solvers are now part of many spreadsheet packages, such as Microsoft Excel. However, big NP-hard problems are usually solved by using heuristic methods, which doesn't guarantee optimal solution, but the solution is very close to optimal. But this one is not covered in this course. Alright, let's continue with example 4.7. Acopal manufactures 3 products: bowl, casserole, and jug. The sales volume for bowl is at least 50%. So let's say this is X1, X2, and X3. So number of bowl, number of glycerol and number of chalk produced. So for the first constraint, x1 must be greater or equals to is at least 50%, so half of the total sales. x1 plus x2 plus x3. So simplify this, you will get 2x1 minus x1 minus x2 minus x3 greater or equals to 0. So x1 minus x2 minus x3 greater or equals to 0. Okay, for the second constraint, it mentioned here, however, the company cannot sell more than 80 units of wool per day. So x1 less than or equals to 80. Okay, and then the three products use one raw material, of which the maximum daily availability is 240 kg. Okay, the usage rates of the raw material are 2 kg per unit of wool, 4 kg per unit of glycerol, and 3 kg per unit of chalk. Okay, so for this one, raw material constraint. So we have maximum availability is 240. So right hand side. So x1 2 kg, x2 4 kg, and x3 3 kg. So 2x1 plus 4x2 plus 3x3 less than or equals to 240. Okay, the unit price for bowl, glycerol and chalk are 20 ringgit, 50 ringgit and 35 ringgit each. Okay, so the objective function should be maximize z equals to 20x1 plus 50x2 plus 35x3. Okay, if we let xi be the number of products produced at the company per day, then the company should solve the LP on the Lindo printout in figure 4.4. A give the optimal solution for this LP. So actually we can from here, so this is the optimal solution. Okay, so from this output from Lindo, the optimal solution is here. Okay, this is the LP formulation. And this one, optimal solution. So for part A, we can see that the Z value is RM 2,800 ringgit. Okay, don't forget the unit. X1 equals to, the value is 40. And x2 also 40. x3 equals to 0. Meaning that Aquapal should produce 40 units of bowls, 40 units of casseroles, and 0 unit of jump to maximize the profit. Sorry, for this case, to maximize the revenue, because unit price, Z value is the unit price, the total sales. So to maximize the sales, this company, Akopal, needs to produce 40x1, 40x2, and 0x3. So that the maximum value is 2,800 ringgit. Okay. So for part B, if available raw material is increased by 120 kg. So this one, right hand side, instead of 240, it is now increased by. So by meaning that you need to plus with the current value. So the new right hand side is 360. Okay. So D1. So for part B, the change is positive 120. So 120. So for this one, you don't need to calculate the range, because we can actually read the range from this output. So since the changes is on right hand side, therefore we need to look at this range, right hand side range for part B. Okay, so T1 equals to 120. We need to check allowable increase. So it can actually be increased by 240 maximum. Therefore, this change D1 is still in the range. So meaning that the current solution remains feasible, but with the new values of BV. Okay. So here you can calculate the new value for Z. So Z value, Z new equals to Z plus 120, the change, and then multiplied by the dual price. So dual price for the first constraint is here. Okay, this one is the first constraint. So here 11.67. So 2,800 plus 120 multiplied by 11.67. So we get RM 4,240 cents. Okay. So here feasibility range. While this one is the optimality range. Okay. So next, part C. Determine the effect of changing the maximum demand for bowl by plus minus 10 units. So for this one, second constraint, it involves at the second constraint, because before this x1 must be less than or equals to 80. Now if there is a change, plus minus 10 units here, plus minus 10 units, so D2 equals to plus minus 10 units. But 42, if we look at the dual price here, if we want to calculate new Z value, then multiplied by dual price. But there is no changes because the dual price is 0. So whether you increase or decrease the right hand side value here, there will be no effect. Okay, as the dual price for the second constraint is 0, there is no effect. Okay, we continue with exercise 4.6. Beauty brooches Sendirian Berhad produce brooches at 2 factories and sells them to 3 customers: Ariana, Aida Juma, and Fariza. The cost of producing 1,000 brooches at a factory and shipping them to a customer is given in table 4.3. So as we can see here, from factory A to customer Ariana, the cost of shipping from this factory to Ariana is 60 ringgit per 1,000 brooches, and so on. Customers Ariana and Fariza pay 200 ringgit per 1,000 brooches, while customer Aida Juma pays 150 ringgit per 1,000 brooches. So here, this is the row I equals to 1 and 2. We have 3 columns, so J, 1, 2, 3. So the variable here is X11, 1,000 brooch shipped from factory A to Ariana. Okay, X12, X13, X21, X22, and X23. So Ariana pays 200 for each unit of X11. Aida Juma 150 ringgit and Fariza 200 ringgit. Okay, and the cost is 60 here, meaning that we want to maximize the profit. So maximize Z equals to Ariana pays 200 and the cost is 60. Therefore, for each unit of X11, the profit is 140. 200 minus 60. So 140 X11 plus 150 minus 30, so 120. 120 X12 plus 200 minus 160, so 40 X13. And then plus 200 minus 130, so we get 70 X21 plus 150 minus 70, so we get 80 X22 plus 30 X23, because 200 minus 170, so we get 30. But there is also a cost that we need to consider, which is cost of labor. So minus 20L. Yes, minus 20L. Because here it is mentioned that additional labor hours can be purchased at 20 ringgit per labor hour. So if the company decided to add labor hours, so you need to consider that cost to be included in the objective function. Okay. To produce 1000 brooches at factory A, 200 hours of labor are needed and 300 hours of labor are needed at factory B. Okay. A total of 5,500 hours of labor are available for use at the two factory. Okay, so here is the final constraint, as you can see here. So the right hand side is less than or equals to, we have 5,500 hours of labor available. So 5,500 hours, and then because there is an option for you to add the labor hours, so plus L. Okay, but because L is also a decision variable, therefore we need to move to the left hand side. So we move to the left hand side like this. Okay, so 200, 200, 200 for factory A, 300, 300, 300 for factory B, minus L less than or equals to 5,500 hours of labor. Okay. Factory A can produce up to 1,000 brooches. So this is the first constraint here. 10,000 brooches is the maximum for factory A. So the total number at factory A is X11 plus X12 plus X13. For factory B, the maximum is 12,000 brooches. So that one is at the second constraint. Okay. So part A gives the optimal solution for this LP. So again, we can see the output here in figure 4.5. So the solution is here. Objective function, so the Z value is 2,000 ringgit and 333 ringgit. Okay, and the decision variables, the value is given here. So x11 equals to 10, x12 0, x13 0, x21 0, x22 11.67, x23 0, and also the last decision variable is L 0. So we don't need additional labor hour to maximize the profit. Okay, so you can list down all of these for part A. Part A, Z equals to RM to, okay, X11 10, and then we have NBV 1 2 13 21 21 23 and L equals to 0. Then we have X22 11.67. So for part B, if it costs 70 ringgit to produce 1000 brochures at factory A and ship them to customer Ariana, what would be the new solution to the problem? So from factory A and ship them to customer Ariana. So this one is referring to a variable x11, first row and first column. Customer Ariana pays 200 ringgit and the cost before this is 60 ringgit, right? Now the cost is 70 instead of 60. Therefore, the change is D11 equals to 130. So this one 200. Ariana pays 200 minus the new cost 70 ringgit. So this is the new coefficient for variable x11 minus the original coefficient is 140, right? So the change is negative 10 unit. So this is the change for coefficient C11 coefficient. So if we look at the LP solver output, we need to check whether it is within the range or not. If it's in the range, then we can just do sensitivity analysis without recalculate everything. Okay. So for objective function range, so for variable x11, the change is negative 10. So decrease by 10 unit. But the maximum decrease is 20 unit. So it can minus negative 20 the most. So negative 10 is within the range. So this one is within the optimality range. Okay. So we can conclude that this shows that the current PV remains optimal because it is within the optimality range. Remains optimal, meaning that x11 equals to 10, x22 equals to 11.67, and the rest is 0. With a new Z value, which is Z prime, equals to Rm 2,330 ringgit and 30 cent plus the change of the coefficient C11 or D11 here multiplied by X11. So we get, I'll continue here, okay. So here, RM minus 10 multiplied by 10. X11 equals to 10, okay. So we'll get RM 2,233 ringgit and 33 cents. So this is the new value for Z. C, if the price of an additional hour of labor were reduced to RM4 ringgit, would the company purchase any additional labor? So the change is for the coefficient of labor variable. So the original coefficient is here, -20. So now it is reduced to 4. So meaning that minus 4, the cost. So minus the original coefficient is minus -20. So the new one is -4. The original one is -20. So the change is equals to 16. From the output here, we can see that the reduced cost for variable L is 19.7333. So reduced cost from the output for variable L is 19.73. Since the reduced cost is still higher than the change thus the company should not purchase any additional labor hour, because this reduced cost L equals to for L equals to 19.73, meaning that if we add 1 hour of labor, it will reduce the Z value by 19.73. Okay. Okay, part D. A consultant offers to increase Factory A's production capacity by 5,000 brochures for a cost of 500 ringgit. So this change, you have an option to add 5,000 brochures for the first constraint. So initially, the capacity of Factory A is 10,000 brochures, right? So now you have an option to add another 5,000, but you have to pay 500 ringgit for the additional. Okay, so for this case, we need to look at the dual price for the first constraint. So here the dual price for the first constraint, if you add one unit, 1,000, meaning 1,000 brooch, it will increase the Z value by 86.6667. Okay, so if we add 5, the new Z value will be added by, so Z can be increased by RM 86.67, so multiplied by 5,000 brooches. So you will increase that value by RM 433 and 35 cents. Okay, but you have to pay 500 in order to add the capacity. So should the company take the offer? No, right? Because the additional Z can be increased only by 433, which is less than the additional cost, RM 500. Thus, the company should not take the offer. But if we change the question to capacity by 5,000 brooches for a cost of 400, then we should take the offer. Okay. Okay, last question. If the company were given 5 extra hours of labor, what would its profit become? So were given, you don't have to pay for these extra hours. So for this case, we can say that the new value for Z would be plus 5. Okay, so labor hours is the last constraint, right? Last constraint. So the dual price is here, 0.27. So 5 multiplied by 0.2667. Okay. So the new value of Z is now 2,334 ringgit and 67 cents. Okay, we still have about 1 hour plus left. So please try to solve this example 4.8 on your own. Alright. Okay, that's all for the subtopic. So hopefully you enjoy this week's lesson, and please don't forget to do this homework, review problems, chapter 4, question 1, A, B, C, D, E, F, and please submit at Google Classroom. Assalamualaikum.